Hello, this is our beam bending presentation. We are group number 23. We are consisting Ik-Jun, Kenny, Peter, and Paul. Here's an introduction. In this lab experiment, we are tasked with measuring deflection of a simply supported beam subjected to a mid-spin point load using two different types of calculation method. We will then use the experimental result gathered through this experiment with the finite element analysis result we got from using a ANSYS to model beam deflection. For a learning objectives, we need to use a Dyer indicator to measure deflection, which is a linear distance. We also need to use a beam tables to calculate beam deflection. And as we mentioned from previous slide, we need to use an ANSYS to model beam deflection. And lastly, we need to operate the Universal Testing Machine, as known as UTM, under supervision to conduct a beam bending test.
So here is the experimental setup. First, we used UTM testing machine to calculate the deflection of hollow beam. And second, we calculate the deflection by using the analytical method by hand. And finally, we can get the simulation data from the ANSYS program. Okay, this is our UTM machine, and as you can see, there is a Dyer indicator in middle point and the left side of the beam. Before we measure the deflection, we need to measure the beam length, beam thickness, each side length of the beam, and distance of supporting point and diameter of support. And then we start to put a load in middle point, and then the deflection was measured simultaneously at the middle point and 5 inches away from the left end of the beam. After finishing the measuring the deflection of each point, we start to calculate the deflection by analytical method. Through this activity, we could remind the thing that we learned in the class. So here is the hand calculation of analytical method. We found the still of the modulus of elasticity as 29,000 kpsi. Third, we learn how to obtain simulation data through the ANSYS, and if we follow it well in order, we could obtain the data well. What's special is that in the tutorial, it wasn't a hollow beam, it was just a beam. But in order to get the actual data, we designed the beam using the data we measured earlier.
The beam we were given in our lab experiment was measured to be at a length of 40.25 inches with an outer height of 2.515 inches and a width of 2.536 inches. The hollowed out beam had a thickness of 0.189 inches, and we calculated its moment of inertia to be 1.629 inches to the fourth power. The beam had a span distance of 14.75 inches from support to support, and a dial placed at the center of the beam and a dial placed 5 inches from the end of the beam lengthwise. The distances of the beam indicators measured from the left of the beam came out to be 20.125 inches for dial 1 and 35.25 inches for dial 2. Here we have loads at 3 different points starting at 7,000, 8,000, and 9,000 pound forces and their respective outputs given to us by the load cell table. Here's the deflection data we gathered at each of the 3 respective output loads from the beam loading table in the previous slide. In the left column, we have the experimental beam deflections which we got from the 2 dials in the experiment. In the middle column, we have the finite element analysis beam deflections, and in the last column, we have the beam table deflection calculations method, with each column being measured at the center of the beam and at 5 inches from the end of the beam.
For an uncertainty analysis, we are tasked to calculate deflection measurement of each dial indicator. The first dial indicator is called MBC Series 1, which was placed at the center of the beam bending, and the result was plus or minus 0.00255 inch. Second indicator is called Go Plus. It was placed 5 inches of left of the beam bending, and the result of the uncertainty was plus minus 0.001601 inches.
In our finite element analysis simulation, we were given 3 different kinds of meshes to look at: element quality, aspect ratio, and the Jacobian ratio. For each different mesh, we recorded the minimum, maximum, and average mesh values along with their standard deviations in this table. These mesh values provided from ANSYS represent how close the element shape is going to be from being a perfect equilateral triangle or a square.
This is a side view of our ANSYS simulation for the deflection. As you can see, the beam deflection is at a minimum at the simple supports and has local maximums at the ends and center of the beam. This is a different view of the same simulation. It is an isometric view. As you can see, we performed this simulation using the maximum theoretical load that we had in the experiment, which is 9,000 pounds of force. This is a graph in MATLAB showing the deflection of the beam with respect to its length under different loads. As you can see, the points where the load curves intersect are the locations of the simple supports. The deflection at both simple supports is 0 from the baseline. Between the simple supports, the curve assumes an approximately parabolic shape, while outside of the simple supports, it becomes linear. Based on the data we gathered from our finite element analysis, we were able to see that the deflection in the beam we had used in the experiment was similar to the ANSYS model that we had created in order to assess how accurate the dial indicators were in the UTM. The purpose of this lab was to assess different acting forces on the beam and how they affected the bending stresses in the beam, and from what we have seen in our data, we have come to the conclusion that there is a linear relationship between bending stresses and the applied loads. The data we have gathered in our table shows that the experimental bending stress responds more than the theoretical bending stress in terms of the increase in applied loads. The ANSYS model had discrepancies in comparison to the test, but could be repeated in future using different settings to yield better results. Dial indicators could be another source of error because the clamp attached to the dial was malfunctioning. Thank you for watching. This concludes our oral presentation about beam bending. Thank you for your attention and support throughout the course.